Good evening and welcome. My name is Bernhard Meyer and I'm the interim dean in the Faculty of Science. I'm pleased that so many of you are logging in to our virtual Gallagher speaker series this evening. We are recording today's session and we will be posting this video on the faculty website. So I encourage you to check our website at science.ucalgary.ca for event listings and video updates. As we come together in these times of physical distancing and virtual connections, I like to think about who I'm sharing this space with, both near and far. We are broadcasting today from Calgary, which is located on the traditional territories of the people of the Treaty 7 region in southern Alberta, which includes the Blackfoot Confederacy, comprising the Siksika, the Piikani, and Kainai First Nations, as well as the Tsuut'ina First Nation and the Stoney Nakoda, including the Chiniki, Bearspaw, and Wesley First Nations. The city of Calgary is also home to the Métis Nation of Alberta Region 3. The University of Calgary is situated on land adjacent to where the Bow River meets the Elbow River, and the traditional Blackfoot name of this place is Mohkinstsis, which we now call the city of Calgary. I also like to take a moment to recognize the Gallagher family for making this series possible. Through their generous philanthropy and vision for deep connections between the university and the community, the Gallagher family has provided the Department of Geoscience and the Faculty of Science with the opportunity to develop and grow the Gallagher Colloquium series. This colloquium program strengthens our scientific community by increasing scientific knowledge, by creating public awareness, and by establishing connections with our alumni, community, students, staff, and faculty. Since 2015, the Department of Geoscience has organized over 25 Gallagher Colloquium talks. The organizers have invited speakers from around the world to share their passion for science, scientific research and discovery, and to help us understand why science is fundamentally important, not only to our own lives, but to the world around us. This year, we are pleased to offer this annual series online, providing us with an opportunity to engage with even more attendees from around the globe. Thank you, Tom and Fred Gallagher, your continued support for this public lecture series and for being champions of science. The Gallagher Colloquium series continues to be an invaluable way to connect science with our community and our community with science. And now on to tonight's event. For almost 50 years, the University of Calgary has been involved in leading-edge space research, working with the Canadian Space Agency and NASA, and building our capabilities and reputation as a leader in space science. The University of Calgary Earth Space Technology Strategy has reinforced the importance of Earth and space research and greatly supports our vision of becoming a great research university. Both the Department of Geoscience and the Department of Physics and Astronomy play a critical role in achieving this goal. At this time, I asked Dr. Eric Donovan, professor in the Department of Physics and Astronomy, to introduce tonight's speaker. Again, thank you for joining us this evening and enjoy tonight's presentation. And with that, over to you, Eric.
Okay, well, thank you, Bernhard. Good evening, everyone. As Bernhard mentioned, I am Eric Donovan, and it is my pleasure to participate in this month's Gallagher Colloquium Series lecture and to introduce tonight's speaker. As a fellow scientist and space enthusiast, I can appreciate the impact space research and exploration has had in advancing our understanding of the universe around us. Earth space science is not one of, but the one research priority of tonight's speaker's home university. And this work aligns very well with the Faculty of Science's priority, understanding Earth's evolving systems. It's a pleasure to welcome tonight's Gallagher speaker, Dr. Fran Bagenal. Dr. Bagenal is a research scientist and professor from the University of Colorado Boulder, and is a co-investigator and team leader of the plasma investigations on NASA's New Horizons mission to Pluto and the Juno mission to Jupiter. Dr. Bagenal received her bachelor's degree in physics and geophysics from the University of Lancaster, England, and her doctorate degree in earth and planetary sciences from MIT in 1981. Her main area of expertise is the study of charged particles trapped in planetary magnetic fields and the interaction of plasmas with the atmospheres of planetary objects, particularly in the outer solar system. Throughout her career, Dr. Bagenal has worked on a number of planetary science missions, including the Voyager Plasma Science Experiment, Galileo, Deep Space One, the New Horizons mission to Pluto, which is part of NASA's New Frontier program, and the Juno mission to Jupiter, which we will learn about shortly. In 2006, Fran was elected a Fellow of the American Geophysical Union, and in 2020, she was elected as a Legacy Fellow with the American Astronomical Society for her contributions towards enhancing and sharing humanity's scientific understanding of the universe. Additionally, her work has been chronicled in numerous television and movie documentary series, such as the 2017 Irish film The Farthest, about the Voyager program, the 2018 TV miniseries called Summiting the Solar System, Pluto Explored, and most recently, the Planets TV series. One other note of interest to add is to the list of recognition and awards is that Fran has an asteroid named after her. We are honored Fran has chosen to spend her evening with us and has agreed to share more about the exciting missions she has been part of in her presentation titled NASA's Juno Mission to Jupiter. Please join me in welcoming Dr. Fran Bagenal.
Thank you very much indeed. And I'm going to get my presentation up, and so I can share it with you. So it is a huge pleasure to be giving this presentation to you. And I wish I could be there in person, but maybe soon I will be able to come visit you in Calgary. So let me tell you about the Juno mission. It's been orbiting Jupiter since the 4th of July in 2016, and we've now had 29 orbits. But I need to explain why Jupiter is so amazing. It is huge. It has a mass of 318 times the mass of the Earth. And as you can see, for scale, it has a radius of about 11 Earth radii. Now, if we take the planet and spread it out, you can see these amazing belts and zones, as they're called. And to give you a sense of what's happening, let me show you the movie. The bottom movie is of Jupiter, taken by Cassini, and the upper one, of course, is Earth. And you can see a lot of interesting similarities and differences. The major difference, of course, is that Earth has continents and land masses, whereas Jupiter does not. And so you can see that the weather system at Jupiter actually tends to be very unchanging. Little spots come and go, but it's very similar in terms of these belts and zones. But then if you look at the Earth, it also seems to have west going and east going belts and zones, but also some circuloidal eddies, some storms that come by and pass over. Jupiter has many more belts and zones, and as we will see, this is related to the fact that it rotates so fast every 10 hours compared with the 24 hours of Earth. So this is a really interesting planet to look at. It's all atmosphere. And when we're looking at it, we're looking at clouds. So the white clouds are ammonia clouds, that they're at the very top and at the lowest temperatures at the top of the atmosphere. Beneath that, below that, we have a mixture of ammonia and sulfur, and that tends to be more orangey. We don't really know what colors the clouds of Jupiter. It just takes a tiny amount of material to cause the coloring. And we think that it's probably some sulfur related materials, but we're not sure. Now, below that ammonia layers, we think there's water below that. Now, let's talk a little bit about the importance of the water. What we were expecting when we sent the Galileo probe into the atmosphere of Jupiter was that we would go through ammonia ice, then ammonia hydrosulfide, and then hit some water. But what we saw when we sent in that probe was in fact very little clouds. So what happened? Well, it turns out that this probe went into what looks like this dark area in the top left image of Jupiter. And this, we think, is a hotspot. It just so happened, we didn't target this, but it landed in a hotspot. And this infrared image taken from the Earth at the same time shows you this bright, hot area that we think we landed in. And so what happened was, just by chance, we went into a downdraft, which was very dry, and we didn't see any water. So the question is, this lack of water, is it due to atmospheric conditions, weather, or is it an indication of lack of water throughout the planet? Now, let me talk you through this rather complicated plot here. What we're interested in doing is thinking about various elements, and you can see the elements along the bottom: argon, krypton, xenon, carbon, nitrogen, sulfur, and oxygen. And we expect in Jupiter that these are all going to be enriched relative to the sun by a factor of sort of 2.5. And you can see these all are, except the oxygen, which is related to water, H2O, seems to be very low. It was down here. And the big question is, what's going on with the water? So why is water so important? Well, if we think about the astronomers' periodic table, the two main elements are hydrogen and helium. And then below that, the next one abundant is in fact oxygen. It's the third most abundant element in the universe. And if we can't find out the amount of water in the largest planet in our solar system, then our ideas of how solar systems form are in a bit of a mess. So this is what we think happened when we made our solar system. You had a young sun at the center, and it was hot close to the sun. And then as you move away, it gets colder. Now, the first materials to condense out of this disk of gas are the rocks and metals. And so you end up making the rocky planets, Mercury, Venus, Earth, and Mars, in close to the sun out of these rocks and metals. And because there's not a lot of rocks and metals in our universe, you get pretty small planets. At some point, you move out past the frost line where water, and as I said, oxygen, third most abundant element in the universe, we expect a lot of water out there, begins to condense and forms the icy cores that eventually capture hydrogen to make the big gas giant planets, Jupiter, Saturn, Uranus, and Neptune. So this is a big issue, is to find out what happened to the water in Jupiter, where is it, how much is there, because this is key for understanding the formation of our solar system. So we designed a mission, a Juno mission, to go out there and find out where's the water, so we can learn how the gas giant planets formed. And since we're flying over the poles, we'll also think about the Aurora, something that I know you guys up there in Canada see a lot of, and is an important factor for Jupiter too. So this spacecraft, the Juno spacecraft, is a very interesting one. It's a solar powered, the first time we've had solar power out at Jupiter. And these large solar panels, you can see there's a person for scale down here on the left. The diameter of these wings is about 20 meters. And then we have the power is about 500 watts generated by the solar panels. And we have this spinning. We keep the panels pointed towards the sun, and we keep it spinning with the radio antenna, which is this thing in the middle where it says gravity science. I'll explain why in a minute. Kept pointing towards the Earth so that we can communicate with the spacecraft, and the spacecraft can communicate with us on Earth. We have some instruments out on the end of the panels. That's where we put the magnetometers. We have charged particle instruments, low energy and high energy, JADE and JEDI, as we call them. And we have wave instruments over here, antennas that measure the radio and plasma waves in the space environment around Jupiter. And we have some spectrometers. We have an infrared spectrometer called GIRAM, a UV spectrometer called UVS, and we have a microwave spectrometer that's on the main part of the spacecraft here. Now you'll see that I've left to last the camera. The camera was just slapped on at the last minute. Oh, I suppose we ought to take some pictures. And you'll see, oh golly, did we get some great pictures. Now, the biggest problem with going in close to Jupiter, and we wanted to get close to take some images and map the planet, is that there is these very energetic charged particles that are trapped in the magnetic field. They keep oscillating up and down because of the tilt of the magnetic field. I'll show you about that in a minute. So we want to avoid flying through these very energetic charged particles in the radiation belts of Jupiter. So we designed an orbit that goes over the poles, ducks under the radiation belts, and skims across the top of the clouds. Now, because of the flattening of Jupiter, it's a bit fatter at the equator than the poles because of the spin, rapid spin of the planet, and it's made out of gas. Then the orbit goes from orbit 1 that is up here, it moves down with subsequent orbits, and orbit 30 is about down here. But we stay out of the radiation belts for as long as possible in these orbits. So the nominal mission is 32 orbits to start with. So what we do is we carefully space these orbits so that we can map out the properties of Jupiter, the clouds, the atmosphere, and the deep interior using these multiple orbits. Now, I was allowed to go watch the spacecraft being built. Here's me wearing one of those bunny suits, as we call them, all dressed up to keep bodily oils and so on off the spacecraft. Very important to keep the spacecraft nice and clean. And you can see the spacecraft here at Lockheed Martin in South Denver, and the engineers are building it. And it takes a long time to build this spacecraft. It took them a couple of years to put all the pieces carefully together. And up here, the top right, is where we're going to put the electronics and protect them as much as possible from those radiation. Here are the solar panels being put together onto the spacecraft. They were folded up so that we could put the spacecraft onto the rocket. And we sent the rocket, we sent the spacecraft out to Florida to go get launched at Cape Canaveral. And of course, like all scientists, we have to have a selfie of us in front of the rocket ready for launch on the 5th of August of 2011. And I'm in there right behind the principal investigator. So a relatively small team of scientists, but behind us are the engineers who built the spacecraft. Probably about 1,000 people built the spacecraft. Now, we didn't have enough oomph with this rocket. It's a powerful rocket, but not quite enough to get us out to Jupiter. So what we did is we did a deep space maneuver, came back past Earth, got another gravity kick, and ended heading out towards Jupiter to get there on what it says, the 5th of July, 2016. But of course, in California, it was the 4th of July, a major firework day for us, a celebration. Now, we were a bit nervous about orbit insertion. We were worried about the engines. We were worried about the radiation, but all went well. We survived the orbit insertion, and we have now done 29 orbits, 29 passes of Jupiter. We're in a 53-day orbit, so we go a long way out, about 100 times the radius of Jupiter before we come back in. Only takes 2 hours to go from pole to pole, but 53 days to complete the orbit. And this allows us to download the data using the antenna to Earth, analyze the data, and then decide what are we going to do next time. So what are we thinking about the interior of Jupiter? Let's talk about the basic properties of this big gas giant. So 318 times the mass of the Earth. And we believe that there's a core inside of about 20 or so Earth masses, something like that. And the density is very high deep down, very low gaseous hydrogen up at the top. Higher pressures, it turns to liquid hydrogen, and even higher pressures to metallic hydrogen. The temperature goes from pretty cold at the surface down to about 4 times the temperature of the surface of the sun, deep down inside. And over here are pressures. This is 1 atmospheric pressure. This is 2 million atmospheric pressures, where we go from liquid hydrogen to metallic hydrogen, and then something like 50 to 100 million pressures, Earth atmospheric pressures or bars deep down inside. So what do these pressures really mean? It's sort of hard to imagine what those numbers are. Well, I'll give you a simple calculation. It's equivalent to 1,000 elephants standing on top of each other in Earth's gravity, with the bottom elephant standing on one leg, balanced on a stiletto heel. So that small area and a lot of mass. And you can imagine that's a huge amount of pressure down there. And that is the pressure that hydrogen is experiencing deep down inside. It's not actually anything we can do experiments on in labs. It's far too high a pressure. And so we have to rely on quantum mechanical models of hydrogen to tell us how the gas hydrogen behaves at those pressures. Now we have some idea of what it might be like inside. I've already mentioned the possibility of the story on the left of this diagram, where you have a core of ice, then you have metallic hydrogen outside, and then you have gaseous hydrogen in the outer layer. But it's possible that the story is actually on the right, where there's mixing of the heavy elements into the metallic hydrogen, and it's all mixed up without a separate core. And so we're going into this experiment with the Juno mission to find out what is it really like inside. So how do we do this? Well, we use a very clever technique. We send a radio signal back to Earth, and we measure very carefully the frequency of that signal. And if the gravity inside Jupiter perturbs the motion of the Juno mission, you can see it wiggling here due to the gravity inside, due to the mass inside, then you get a shift in that frequency, and we measure that Doppler shift. And that tells us what the effect of Jupiter's mass distributed inside the planet, how that affects the motion of the spacecraft. And so we can measure the distribution of mass inside Jupiter. And this is a really key, important technique that we can use. And what we have learned is that indeed, there is not a very distinct core. Things are much more mixed up. It's probably a little even more mixed up than in this cartoon here, with the heavier elements, the oxygen, the carbon, the iron, the calcium, and stuff like that, mixing in with the hydrogen up to maybe half the radius of Jupiter. Why that happens? Good question. The people are scratching their heads trying to work it out. We also see that, in fact, helium, which you remember is the second most abundant element, seems to be raining out of the atmosphere and is depleted from the uppermost atmosphere. So the bottom line is that we don't have the distinct boundaries that you see in the classic textbooks, and the boundaries tend to be are probably much fuzzier than those textbooks would suggest. Now let's move on to the magnetic field. We're going to fly through the magnetic field of Jupiter and try and work out what it's like inside. And to measure that magnetic field, the interior magnetic field generated in the dynamo deep inside. And what we think is happening is this. When you take hydrogen and you make very high pressure, so 2.5 million atmospheric pressures or megabars, what happens is, instead of the hydrogen being molecular hydrogen of 2 protons and 2 electrons bound together in a molecule, what happens is at those high pressures, the protons and the electrons get separated and they can move relative to each other. And so you can see, if you have charges that are able to move, it becomes electrically conducting. And this is important because one of the primary things you need for a dynamo is to have a large volume of liquid that is electrically conducting. You also have to have a source of heat that will turn it over and drive a convection. But there's plenty of that in Jupiter. So we have a very strong magnetic dynamo. We have a model here on the right. We don't know for sure whether this is exactly what it looks like inside, but Juno is going to tell us exactly where this dynamo is and hopefully tell us a bit more about the flows that lead to this very strong magnetic field. Now, when we talk about magnetic fields, it turns out that Earth and Jupiter both have magnetic fields that are tilted by about 10 degrees. Earth, it's more like 11, Jupiter, it's more like 9.6. But you can see there's a sort of like bar magnets in the center of the planet. The difference is that right now, the current polarity of the Earth's magnetic field is the opposite to that of Jupiter. But you know very well that the Earth's magnetic field every 200,000 years or so flips occasionally. We don't know about Jupiter, but the current polarities for Jupiter and the Earth are opposite. Now, when you get closer, you see more complexity. And here, when we look at Jupiter's magnetic field, and this is from 9 orbits of the Juno spacecraft, you can see that the north and south look very different. The south is much more regular, and the north seems to have a magnetic anomaly, this very strong red region up near towards the poles. There's also this light region near the equator that is a weak magnetic field region as well. Over here, there's a weak one over here and then a stronger one over here. And so when you look closely, you see a lot more structure. And indeed, looking at up to 24 orbits, we've now got a lot more structure, and you can see how this blue spot, as it was, is developing more structure that we can see in this weaker region over here. So as we move into, we hope to have an extended orbit that will go beyond the original 32 orbits up to 75 for 5 years, the next 5 years. And if we're applying to NASA right now for the extended mission to get some funds to do this. Hopefully they will do so. But you can imagine we're going to get a lot of really fantastic data as this orbit precesses up towards the north and we map out the magnetic field. In particular, if you look at this magnetic field model, that shows you this idea of the wires coming out. Those are the magnetic field lines. You can see the red North Pole anomaly, and then you're going to see the blue spot coming around in a minute. Here we go, of this anomaly near the equator. And we want to measure this in more detail. It's perhaps telling us something about the dynamo at Jupiter. Yes, this is unfortunately an accident of there we are. But the point is, just ignore the movie for a second. What we want to do is, by looking at the depth of dynamo and combining that with interior models, is to understand what's going on inside. Okay, so let's think now a little further above the dynamo region. Let's think about the atmosphere. Remember, one of the big things we want to know is where's the water and what is driving the wind system, those belts and zones that we saw in the movie at the beginning. So what's going on here is that we have heat from the inside that is driving convection and carrying the ammonia up. And as it goes up, it begins to experience the rotation of Jupiter, the Coriolis force, that then leads to these belts and zones, these east and west belts and zones. So you have ammonia here at the top where the hot air rises, and then between the clouds, we can look deeper down and see the ammonia reddish hydrosulfide. Now, visible image on the left shows you the belts and zones that we see, those ammonia clouds at the top. And then an infrared picture shows you the bright regions are where you're looking deep into the hotter regions. And in infrared, the darker regions are where it's cooler. And we use this technique looking at different wavelengths. This is a Juno series of images taken with a Junocam instrument, and you can see all sorts of structure now And this is telling us about the dynamics of the interior of the atmosphere just below the clouds that we can see with infrared. But to see the dynamics below these clouds, we need to not only look at infrared, which is this picture on the right, but the infrared only really penetrates down to about 1 bar. That's about 50 kilometers below the cloud tops or the upper layers of the atmosphere. What we want to do is to use longer wavelengths, use microwaves, and we have 6 different channels on Juno that will go down, deep down to pressures of something like 100 to 1,000 bars at depths of about 200 kilometers, maybe 300 kilometers in depth. And so we hope to use that to map out the water. Now you may say, why microwave water? Wait a minute. Yes, you got it. How do you heat your cup of tea? You take your water and you put it in a microwave oven, turn the microwave on, and the water absorbs microwaves. We know that, obviously, that's how you heat up your cup of tea. So what we're going to do is fly over Jupiter and measure the absorption of microwaves coming from the deep interior as they come out, and then measure it by Juno as Juno flies over the planet, and that will allow us to map out the water. At least that was the idea. So what did we see when we started mapping out with the microwaves what the atmosphere is like? And what we actually found was that the distribution of microwaves getting out was very irregular. And indeed, by looking at the different wavelengths, we noticed that the ammonia seemed to have a very deep circulation. It was not the simple multi-layered structure that we thought it was. There seems to be deep circulation extending from minus 350 kilometers up to the cloud deck. So here is a movie taken, a series of different microwave measurements from different passes, and it's going from the top down to about 300 kilometers in depth. And you can see that there's a variation from orbit to orbit, and there's certainly, it's not a uniform, simple layered structure. So it suggests that the convection extends really quite deep. So it's not this simple picture that the textbooks draw of very thin layers of clouds without any mixing between them. It's not so simple. In fact, what we think is happening is that there are mush balls. Yes, mush balls. Let me explain what those are. So you have an updraft, an area where it's hot. And so at the equator, that tends to be, that is an area that we have that. And it carries water up. And as the water goes up, it cools off and it condenses, just as it does in Earth's atmosphere, to make water crystals. But those water crystals mix with ammonia in the outer layers of Jupiter's atmosphere. And so you end up with these mush balls, which are the interior is in fact ammonia with water ice on the outside. So you make water droplets, or sorry, ammonia droplets, and then on top of the ammonia droplets, the water ice crystals form to form these mush balls. And they're on the order of, I don't know, baseball size, 10 centimeters or so across, we think. And they go down eventually as they get really heavy. And as they fall down, they get really big, they fall down, and in fact, go deeper than the water layer. So this shows you that there's a vertical mixing that is really quite complicated with updrafts, condensation, downdrafts are carrying these solids down deep. Now, we know that water has to be involved, and water in solid form as ice, because we see lightning, and lightning is a big indicator of moving water crystals moving relative to the clouds around it. And so we detect the lightning using either as flashes of light or using the radio signals. So we're learning of this complexity in the atmosphere, a lot more mixing and more complex vertical mixing of material, a lot more structure and a lot more dynamics in the atmosphere. So this, of course, is going to complicate how we derive global water abundance if we've got to deal with all this complicated weather systems. Okay, so let's move on to the fun part and have a look at the images that have been coming down from the Junocam instrument. Now, it's very interesting that this was added on as a sort of community camera. It's a citizen science camera, and we download the images and you can go to this Junocam website and you can look at the images immediately, and then you can download them, you can play with them and do what you want, and then post them back up again. And so it's a real communal effort, a worldwide involvement of people in analyzing the data and playing with them. So here's an example of what some of the amateur scientists have done. They've taken the true image on the left, which is a typical color that is realistic, if you like, coloring for Jupiter's atmosphere, and then cranked up the color contrast to make the one that's below. And you can really see that when you crank up the color contrast, you can begin to see a lot more structure. And so that's a game that people have been playing, trying to understand what's going on in Jupiter's atmosphere. And here are two really beautiful close-up images that we have obtained with Junocam of the atmosphere of Jupiter. And my golly, look at all that turbulence, look at all that structure. We had no idea that it would be that level of structure in the atmosphere. And then the scientists play with it, but so do the artists. The artists have a lot of fun. They take these images and play with them. And look at this Van Gogh. Isn't that brilliant? So I think it's great that the scientists and the artists are sharing this data from Jupiter and playing with it and having a lot of fun, as well as doing some science. So here are a few more nice pictures. You can see the dramatic swirls, these eddies, these storms, a lot of complexity in this atmosphere. Here is one that's less exaggerated in color, and I think is very aesthetic and beautiful, with a big storm that has formed relatively recently in the middle of this picture. We flew over the poles for the first time, and we have polar pictures at Jupiter, but you have to remember, looking at these pictures, that because it's a spinning spacecraft, we get slices as we're moving very quickly from north to south over the planet. And so to make these images, you sort of have to put some of the images together to make a global view of what Jupiter looks like. But you can see these blue clouds in the upper layers of the polar region are blue for the same reason the Earth's sky is blue. It's scattering of the blue wavelengths of sunlight. Now, if we look at the infrared with the Junocam instrument, we can see the South Pole. We see these vortices, and you'll see at the south we have 5 around a central vortex. The north we have 8 around a central vortex. We don't know why there's a number, one number versus another, but it is true that it has stayed this way now for a couple of years. Now, in some ways, it's a bit like what we see at Saturn's polar region with the Cassini mission. Saw a hexagon with a central vortex in the middle, and maybe we see less structure in the atmosphere because the clouds are deeper on Saturn. It's less massive, a third the mass of Jupiter, but we do see at Saturn this nice hexagon around the pole. So why one is a hexagon, the other is multiple vortices, we don't know for sure yet, but this is really something that is getting the atmospheric dynamicists having some fun and exploring. Now, this is one of my favorite pictures of the atmosphere. Nice furry cloak. It shows the haze over the poles with a furry blurred image below. But it's something that makes me feel warm as winter approaches. Here are some more pictures of these vortices. Sometimes we have bright colors at the center and dark around it. Sometimes it's dark at the center and light around it. These are all things that the atmospheric dynamicists need to start modeling and explaining. Now, because we're moving fast, we're not able to stop and stare and take movies and watch the motions, unfortunately. And we only come back every 53 days. And so it's hard to actually measure the dynamics. But you can see that it really is a very dynamic atmosphere. And you can see all these structures. This is towards the polar regions. Here's another region that's got, you can see these white strands and then darker regions below. And these white ones are what we call pop-up clouds. And you can maybe get a sense looking at these images that these very white clouds are fresh ammonia clouds that are sticking up. You can almost see shadows here when the lighting is oblique. And then the darker clouds are deeper in the atmosphere. So this is a picture I took out of the plane in the days when we were flying around, and because this reminded me of those pop-up clouds on Jupiter, and I think it's very similar, these convective cells bringing up fresh moisture that condenses to make these clouds. Here's one of my favorites here, showing you the dynamics again with the east and west flows and the vortices being produced in these wind shears. Here's a very dramatic version of the atmosphere, again, showing you a lot of turbulence. Look at these multiple vortices up here. There's lots of vortices, a lot of storms. And here's another one, again, with some more pop-up clouds in the fresh regions of ammonia clouds. And this one is close to the terminator, where there's a shadow off to the right, sun to the left, and you can sort of now really get a sense of the three-dimensionality of these clouds. Here's a more recent one showing similar sort of structures. And then sometimes people have been looking at the clouds and seeing features. I love this one. This is the owly eyes, one of my favorite pictures. Of course, that's just temporary, but humans have loved looking at clouds and imagining shapes. And here's Danny the dolphin. Look at that. I'll zoom in on Danny. You can see maybe a pelican here and maybe a dragon chasing him. A lot of fun. It didn't last very long, but a beautiful pattern in the atmosphere of Jupiter. Now, we need to talk about the Great Red Spot. This is an image that was taken with a Hubble Space Telescope. It had a big global view, a really beautiful picture taken from Earth orbit. And yes, that is Io, the innermost of the 4 Galilean moons off to the left. But the Great Red Spot has been observed for hundreds of years using Earth-based telescopes. And Voyager stared and over many days was able to take this movie of the Great Red Spot. And what we're looking at here is a high pressure zone with circulation going around. And the size of it at the time of Voyager was about 2 Earth diameters across, and the circulation was about 6 days. Of course, this is what Juno found, or rather the artist's interpretation of what Juno found. Why not have some funny? But seriously, what's interesting about what Juno is finding about the Great Red Spot is that it's shrinking. It's getting smaller. And, you know, Hubble had been telling us that it was smaller than the time of Voyager, but this really shows how much smaller it really is. It's getting rounder. And with this close-up that we see with Juno, you can see the dynamics around the Great Red Spot. Here's a beautiful picture showing you the turbulence sort of downstream of the Great Red Spot. Here is a somewhat of an artificial animation, but gives you a sense of what's going on in the Great Red Spot, that high pressure region. And Coriolis causing it to spin around like this. Now, what the amateur astronomers, I don't like calling them amateur astronomers because they are just so clever and brilliant people, citizen scientists. What they do is they take pictures from their telescopes at home and of Jupiter, and then they look at the dynamics night after night. And then, because they can access the Juno data and compare with Juno data, they've been very actively involved with looking at the Juno data and relating what they see in their backyard telescopes with what we see with Juno, and been very helpful in explaining the atmospheric dynamics that we see. Now here is further evidence of the Great Red Spot getting smaller, and over time it's still shrinking. Now technically, if you just took, or mathematically, if you make a prediction based on Voyager through Juno, it should be disappeared by 2050. On the other hand, maybe it'll just get bigger again. Maybe it'll break up. We don't know. And so with the extended mission over the next 5 years, we hope to be able to carefully map out the structures and measure how it is evolving over time. It is indeed very deep. We can use the microwave measurements, and it shows us that indeed the Great Red Spot extends for something like 150 kilometers down. So it's a really really deep funnel that goes down into the towards the deeper parts of the atmosphere. So here's one more picture, and I just have to say that's not bad for an outreach camera, eh? It wasn't designed to do science, but it's doing both fantastic science but also beautiful images. Okay, lastly, I want to tell you just a little bit about other things we're looking at. This is a Hubble picture of the Aurora, and you see footprints associated with the satellites, the main auroral emission. Here's a movie from Hubble, and you can see the Aurora from EO associated with EO here, dynamics in the side. And this is what we're seeing with Juno. We're seeing in the north and the south, very different shapes. We're seeing the magnetic anomaly in the north in the shape of the Aurora. We look in the infrared and we see a lot of structure. And if we compare the infrared and the ultraviolet, we see very different structures when we're looking at the same time over the same region. And that is telling us something about how the energetic electrons are bombarding the atmosphere and telling us a bit about the atmospheric chemistry. Now, Jupiter has this very strong magnetic field, and it extends a long way out past the planet. And indeed, you could put all of the Earth's magnetosphere into the planet Jupiter. And so this magnetosphere is very large and rotates every 10 hours. And the most important thing is the moon Io plays a major role. We've known since the 60s that Io triggers radio emission. We've been seeing this for a long time. But now when we look at Io, we are beginning to see its role in the magnetosphere. We've seen, this is a New Horizons picture of the Tvashta eruption. And now this is the Juno images showing you the volcanic activity on this little moon. It's the same size as our moon. And so Io, this innermost Galilean moon, ejects about 1 ton per second of volcanic gases, sulfur and oxygen and sulfur dioxide, and it generates 1 million amps of current that go between the moon and the planet Jupiter, exciting the aurora that we saw in the atmosphere of Jupiter. So Juno is flying over the polar regions of Jupiter. It's measuring the waves, it's measuring the magnetic field, it's measuring the charged particles, it's looking down on the aurora and relating the dynamics of the aurora with the variations in the field, particles and fields that we measure on the spacecraft. And so what we're learning with Juno is we're mapping out the atmosphere, we're mapping out the dynamics of the lower atmosphere, we're measuring the distribution of mass inside, and we're getting a sense of how Jupiter is constructed. And we hope by the end of the mission to get a better sense of how it's working inside. Now, of course, the first thing we've learned is it's not as simple as this picture. It's much fuzzier inside, and we need to make a new cartoon. And with that, I'll thank you very much and take questions.
Okay, just give me one second here. That was a thank you, Fran, for really an incredibly inspiring talk. There's a few things that strike me about your talk. First of all, the fabulous images, and you know that we're involved in the SMILE mission, the future SMILE mission here in Calgary, and just last night, like, we had a meeting between Europe, Canada, and China, and so I was up at like 3 in the morning giving my talk. But last night we had a debate about whether or not we're going to put a public outreach camera on SMILE, and so I'm taking part of your talk and bringing that to people for that discussion. Okay, so thank you for that. I think it's amazing also that it just strikes me as kind of personally amazing that we live, I probably won't live to see it, but really within our lifetimes, it's, the red spot's going away.
I know.
Which is kind of amazing, right? It's just a sort of permanent feature of Jupiter. Well, not so much so, okay? So we're going to do a question and answer period now, and I'm looking at the chat there. And do we have any questions yet from people in the audience? So Megan Sharp, how long do some of these big storms last? For example, storms on the scale of the ones you pointed out in the citizen science art projects.
Well, they vary. We don't know. That this is a little bit of a difficulty. We can look at some of the big structures like the Great Red Spot, and there are a bunch of other ones, the big, large white spot and so on and so forth. And the amateur astronomers can see these with their telescopes, or Hubble can look at them and so on and so forth. And Juno gets up close and sort of measures the local dynamics and so on. But the problem is we can see longer term things. What we don't see is the short-term behavior that comes and goes, because our orbit is 53 days. So if one of the storms changes dramatically over 53 days, it's gone by the time we come back. So, Danny the dolphin had gone by the time we came back, and there was nothing we could do about it. And so, that's the way it goes. On the other hand, when we look at the Great Red Spot, we know it's been there for hundreds of years. And we look at the polar vortices, we know they've been there for a long time. So, the answer is the bigger ones last longer, the smaller ones go away quicker. But that detail is, the actual quantifying of that is work to be done.
Okay, thanks, Fran. I'd really love more questions from the audience, but I've got a couple of things myself. So first of all, can you, and by the way, Megan says, fantastic presentation, Kamali Abelson asks, fantastic presentation, can't wait to see more. So glad you put the camera on the Juno mission. It certainly builds passion for science. Okay, and that's not a question, it's a comment, and certainly I can't imagine anyone disagrees. I have a question, which is, you talk about the 53-day orbit, and what that does is it gives you a time to plan the next pass, right? And I'm wondering if you could just comment a little bit about what that's like, because I can imagine that that's pretty stressful at times, right? And secondly, how much of the orbit, how many hours of the orbit is really scientifically useful?
Every single minute is scientifically useful, because of course, for most of that 53-day orbits, it's out in the magnetosphere. Okay. And that's exactly what I'm interested in. And I have colleagues working with me and mapping out the structure of the magnetosphere. It's only 2 hours to go from pole to pole. Yeah. So that's sort of like going around the Earth 10 times in 2 hours, I think, if that's the right number. Anyway, it's moving fast at the equator. Now, in terms of planning, it actually is not so bad, because we map out, we have a very regular spacing of our orbits because we want to map it out very carefully. And we have fairly straightforward observations that we make. So it actually is not too difficult to do the planning. I mean, there are occasionally opportunities to get close to a flux tube of Io, or actually get close to a satellite eventually when we get closer to later in the orbits. But it's pretty easy actually to do the planning. It doesn't take us that long. It's
good.
Yeah.
And I agree with you on the magnetosphere too, by the way, of course, right? So Michael Briscoe asks actually, you know, a question that a lot of people probably have is what exactly causes the footprints in the Aurora, the magnetic field pulling electrons from the ejected moon gas into the poles?
You can think of these moons as being conductors moving through a magnetic field. And so, as you've probably done, and you can easily do at home, if you take a magnet and you take a wire and you put a voltmeter across the wire, you can move that wire through the magnetic field and you will produce a current flowing along that wire. And so it's the same sort of thing in principle. Of course, the devil's in the detail, but in principle, it's the same thing. The moons are conducting, they move relative to the magnetic field. Actually, the magnetic field sweeps past them, and you induce a current. You have an induction current that moves along the magnetic field, the electrons flowing along the magnetic field. And when those electrons hit the atmosphere, they excite the atmosphere and make it glow, just like the Earth's aurora.
Okay,
Except
I've got
it's hydrogen glowing, not oxygen.
So I've got a few questions. One that was texted to me actually by our Vice Dean of Science, Cindy Graham. And she has, first of all, just an amazing presentation. Loved it, love. Okay, that's her comment. And her question is, what advice would you give to a woman considering a degree or career in science?
Do it. Follow your passion. Get involved. Ask questions. Keep asking questions. Be persistent. So the cost of this mission is it's basically $1 billion, 1,000 million. It's $1 billion. You divide that by the population in the US, it's a cafe latte per taxpayer, okay? And I think it's worth every penny because it gets kids to do their math homework, okay? And to go into science and be excited by science. And so, my advice is stick with your passion, get involved, ask questions, and stick with it, and do your math homework.
You'll tell my son later that, by the way. And you know, it's interesting because I remember when Congress wanted to shut Hubble down, and school kids from all over the US were sending in bags of coins.
Right.
And that actually stopped the shutdown. So Parnius Shokri asks, does the magnetic field of Jupiter protect the inner planets like the Earth?
No, it's too far away for one reason. And so the magnetic field of Jupiter does not come close to the Earth. The other thing is the tail goes away from the sun. And it turns out that the tail of Jupiter extends all the way to the orbit of Saturn. And we know this because when Voyager went from Jupiter to Saturn, it went through the tail of Jupiter's magnetosphere, which is amazing, right? So it's really this long tadpole, if you like, but it doesn't go near the Earth. It may send a few energetic electrons towards the Earth. There are some people who argue that.
Okay, thank you. And then Ian Watson is asking, is the magnetic anomaly identified in the equatorial region associated with the Great Red Spot?
Excellent question. And they call that magnetic anomaly the Great Blue Spot. And it annoys the heck out of me because it's purely a factor of what you choose for your color scale when you make a plot of the magnetic field. I mean, magnetic fields don't have color, okay? So it's really confusing to call it the Great Blue Spot, and because people confuse it with the Great Red Spot, and it has nothing to do with the Great Red Spot. I mean, that's an obvious question that people ask, is it related in any way? And the answer is no. Different part of the planet, and not dynamically related either.
So Thomas Gallagher, whose name is associated with this
I recognize the name, yes.
and asks, can you elaborate on the magneto-electric effects of Io and the Jupiter coupling?
Yes. So, you know, this is something that I've been fascinated with from the beginning. And Voyager flew directly below Io. And of course, Voyager was really detected the first eruptions on Io and detected the big plumes on Io. And it was Voyager that detected the ton a second that was pouring out to make this big plasma, big donut of charged sulfur and oxygen. And I did my thesis on the Voyager measurements as we flew through that big donut of gas. But what's interesting with the electrodynamics is that, in fact, it's not really a wire, as in a fixed wire that goes from Io to the planet. It is, in fact, a wave. It's an Alfvén wave. Eric knows what Alfvén waves are. But it's like taking the magnetic field and plucking the magnetic field and sending a wave along the field towards the planet. And that wave accelerates electrons. And those electrons that are accelerated by those waves are what hit the atmosphere and excited the aurora. Now those waves bounce then, they bounce back and they go back and forth and back and forth and back and forth. And so that region, that orbit of Io is filled with these Alfvén waves and accelerated electrons that bounce back and forth and excite aurora when they hit the atmosphere of Jupiter on either end. So it's a really interesting phenomena, and Juno has flown through that flux tube and measured directly those charged particles being accelerated and the waves. So it's actually turned out to be a really interesting phenomena, and the process of those electrons being accelerated back and forth then radiates radio emission. And it's that radio emission that we've been observing here on Earth since the 60s. So it's a really fun story.
So that's great. So Glenn asked a question that you are undoubtedly being asked by NASA. What do you plan to do if your mission is extended?
Oh, so this is kind of fun. What we're going to do is the orbit will begin to precess downwards. You know, I showed orbit 1, orbit 15, orbit 30 or something. And what will happen is we will cross the equator where the moons are. So we're going to fly past the moons and make all sorts of observations of the moons. And we will go through this donut, this Io plasma torus of sulfur and oxygen that comes from Io and becomes ionized in the environment around Jupiter. We'll fly right through all of that and make those measurements. We'll also be making measurements, more measurements of the magnetic field and the gravity field, and that will tell us more complexity. As I keep saying, the closer you get, the more dense your measurements, the more structure you always find wherever you go in the universe, whether it's seeing sunspots on the sun or going and looking at galaxies. The closer you look, the more details you always see and the more structure you see.
Wow. Okay, so let me just, the questions are now pouring in. So Terry Ray Ricky asks, is there any possibility that the microwaves being used for measuring could have any impact on the movement of the gaseous layers due to heating up the water?
It's a passive microwave. So I'm not 100% certain about your question. So the microwaves are generated deep inside the planet because it's hot inside. And the microwaves come out and they're absorbed by the gases, particularly the water and also the ammonia, before we detect them out here. Now, those outgoing microwaves, yes, they do interact with the water and they interact with the ammonia. And so, yes, they will be involved in heating those gases. But the heat coming from Jupiter is pretty uniform from the interior. It's not like it's a beam that's being directed at one particular location. And so it's important to have the heat coming from below and driving the convection, but it's not quite like a laser pointer where you have beamed energy. I hope that answers your question.
I think that, I believe that is the answer that she was after. And so Stephanie Round asks, are there any ideas as to why the red spot storm is so deep, large, and has lasted so long?
No idea. No idea. I asked this question of the experts and they go, blah, 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 blah. They don't know. We don't know. We've got a lot of work to do. I mean, we do our atmosphere, Earth. We have people who develop complicated models of the Earth's atmosphere. And it's hard to make predictions more than 3 or 4 days, maybe 5 days at most. Weather is tricky. Weather is difficult. And just because it's a big rotating, fairly simple with no continents, you can see that the dynamics we're discovering with with Juno, with those mush balls and the convection, it's pretty complicated. And so why you end up getting a really big, deep storm developing is a very important point, but we don't know the answer to that.
Okay, that's there's another question here, which I want to get this right. Okay, so is our cool Jupiter, I think temperature-wise, unique with its larger orbital period versus the amount of hot Jupiters with shorter orbital periods detected so far around other stars?
Okay, so until we started finding planets around other stars, we thought all the solar systems would be like ours. And you would have this formation with an ice layer that you would form the cores of the giant planets out where Jupiter is. And then you'd have Saturn, Uranus, Neptune, and then we'd have the rocky and the planets. And we thought all solar systems would be like our solar system. Then we began to find these solar systems where there were objects the size of Jupiter, or many times the size of Jupiter, that are close to the star. And people began to say, what's going on here? Something weird. And so they began to have ideas. Maybe the gas in that disk hung around and the drag on the Jupiter caused it to go in towards the sun, the star, the local star. Okay, that kind of makes sense. And then we started thinking about Uranus and Neptune. This idea of migrating planets became important. And we began to think of Uranus and Neptune. You can't make them where they are in the life of the solar system. You probably had to have them form near Jupiter and they migrate outwards. And so the point I'm trying to make is, by looking at other solar systems, got us thinking, planets don't necessarily have to form where they are right now. Maybe they form somewhere and move around. And so there are ideas related to what we're finding at Juno, related to the distribution of mass inside, that maybe the formation of Jupiter is a bit more complicated. Maybe it moved around a bit when it was forming. And there are ideas out there, a very active field, exciting field right now. How do you make our solar system? And then, of course, we have to think about how do you make other solar systems. So indeed, it was not the simple picture that we thought we would confirm with Juno, but the Juno results are getting us thinking and coming up with ideas.
Okay, so thank you. That was Thomas Alex, by the way, who asked that question. Now, this is going to be our last question, and it's a question from Tony Copping, and I'm going to then pass you over to Chris Clarkson. But I want to remind people in the audience, especially there's one more question on deck, but other people, if you have questions, just stick around after we close up, and we'll take a break for about 20 seconds, and then Fran will answer some more questions. She's been gracious enough to offer her time that way. So Tony Copping asks, does Juno need to do maneuvering to change the orbits, or are the orbits precessing naturally?
It's all happening pretty naturally. We do little trim maneuvers, not very much, but basically we put it into a fairly stable orbit and it just goes like that. Now, if we get funded for another 5 years, we are actually going to shorten the orbit a little bit and change things that will allow us to optimize our observations. But we don't have to do a whole lot of firing of the engines. And, you know, it makes it a lot easier for making observations if you don't have to constantly change your spacecraft motion.
Okay, thank you, Fran. And again, for Lauren, who asked a question, and others, Fran will stay around after we wrap this up. Over to you, Chris.
Hello, everyone. I'm Chris Clarkson, a professor in the Department of Geoscience. I'd first like to thank Dr. Bagenal for her thought-provoking and beautifully delivered presentation. I know that the next time we have a hailstorm in Calgary, I'll be thinking about mush balls for sure. Given these challenging times, it's always nice to be reminded of the amazing accomplishments of humanity in the arena of space science. Your passion for scientific space missions and exploration has probably ignited a similar passion in a few of the members of the audience this evening. I'd also like to take a moment and personally thank the Gallagher family for their ongoing support of this public lecture series. Our students, faculty, and staff and alumni have all been made richer by being able to learn from world-class researchers like Dr. Bagenal and scientists who have presented for the Gallagher Colloquium over the past few years. As you heard earlier, the University of Calgary has been involved in space research for nearly 50 years. If you're interested in supporting our space research program or any other faculty initiatives, please visit our faculty website at science.ucalgary.ca. Additionally, there will be a link included in the post-event survey that you can follow. Please remember to register for our next Gallagher presentation on November 19th and spend a night at the Royal Tyrrell Museum with Drs. Darla Zelenitsky, Caleb Brown, and Francois Terrien. On December 4th, the Department of Geoscience is hosting the Tom Oliver Lecture with invited speaker Dr. Peter Kellerman. He'll be talking about CO2 capture and storage via carbon mineralization. Save the date and plan to register when you receive the email invitation. Final housekeeping note for the evening. When you see our event survey in your inbox, please take a moment to fill it out. The link to give will be included in the survey in case you're interested in doing so. Your feedback is important and we want to hear from you. Before we formally close this evening's event, I wanted to let you know that Dr. Bagenal has offered to stay on the Zoom webinar a bit longer to answer any further questions that you might have. We'll begin our extended Q&A session momentarily. First, we'll pause for about 30 seconds to allow those who would like to log off for the evening to do so. Again, thank you very much for tuning in tonight and enjoy the rest of your evening, everybody. Back to you, Fran and Eric.
Okay, you'd think after all this time I know how to unmute it, instantly, but it always I stumble a little bit with that all the time. So, so what? Let me see now. I've got some. Yeah, I've got. You're going to be here for a bit of time, Fran. Sorry. So Lauren Boron asks, what are your personal hopes or goals for future Juno missions or specific studies of Jupiter?
Well, I want to fly close to the satellites and measure that interaction of the plasma, the charged particles that are trapped in the magnetic field with those moons. And we'll get a chance to do that with the extended mission. That will be important. We'll also do a very clever thing where we take the radio signal and we put it through as it goes behind the planet. It will make an occultation measurement of the ionosphere, the ionized region of the upper atmosphere of Jupiter. And this is a technique that I'm sure Eric knows is used, and it is used throughout the Earth. Understanding the Earth's upper atmosphere is to use radio signals, and as they pass through the ionosphere. We'll do that, which will be really important because we don't know what the ionized region of the upper atmosphere of Jupiter is. And that's key for understanding the auroral processes. So those are some of the ones that I personally am very interested in. I also really want to know just how complicated that dynamo is. And is it changing with time? Can we measure that? I don't know. We'll see.
Okay, thanks, Fran. I'm sorry, people are texting me how good your talk is.
Questions, yeah.
So Ben Titolo from our geosciences department asks, there's been a lot of chatter in the physics community in recent years about the properties of solid hydrogen. Do Juno's observations offer any insight into its properties that could help to understanding this?
So I have a feeling you may be referring to some stuff that's been in the press about diamonds in Jupiter. Maybe you are, maybe you're not. That's actually carbon rather than hydrogen, but there is some question about solid carbon turning into diamonds deep in the high pressure. Remember those 1,000 elephants standing on top of each other with a bottom one and a stiletto heel, the pressure at the center of Jupiter. I find that very unlikely, but because you have to sort of focus the carbon together to make those diamonds. With hydrogen, it probably isn't solid. Solid is probably not the right term to use. Very, very dense liquid or fluid is probably the right term to use. The problem is we do not know the equation of state. That is the functional form that relates density, pressure, and temperature, which for simple gases you learn in physics classes and you have an equation of state. But when you get to these high pressures, it's really hard to know how these materials behave. You can do experiments in labs where you use lasers and you can have for a very small time a high pressure, high density region, but we can't get to the pressures that are at the center of Jupiter. You know, yeah, we could get 1,000 elephants and put them on top of each other, but realistically, it's not possible. So we will make all these measurements about the interior of Jupiter, but there will be a lot of uncertainty depending on the models that we need to use to describe the hydrogen, the equation of state of hydrogen. And so we will rely on quantum mechanical models, and they're not perfect. And it'll be an iterative process, right? So you make some measurements, you do some modeling of and then you test them against your measurements, and so on and so forth. It's messy, but science is messy. Hope that answers your question.
Okay, so Robin Owens is asking, in James Gleick's book entitled Chaos, there is a numerical model of how the red spot on Jupiter formed. What do you think of this?
Oh, I read that book a long time ago. I haven't read it recently, but now that you tell me that it mentions the Great Red Spot, I'd completely forgotten that it mentioned the Great Red Spot. I'm going to have to go back and read it again. I think the chaos is a very sexy word, isn't it? Right? But really what we're talking about are nonlinear phenomena that had feedback systems. And I think weather is one of the classic examples of nonlinear feedback systems, right? And so there is, what that means though, is that it's really hard to predict. And so there's always been this sort of thing with the weather at Earth, there was a sort of description that if a butterfly flaps its wings in China and it can relate to storms that experienced on the US. Now it's a metaphor, it's not literal, but the point is the same with the weather on Jupiter, more so than we appreciated before Juno. If you look at Juno, you really understand non-linear feedback systems because the turbulence is clearly iterative and working on itself There are all sorts of feedback systems. You can also imagine, if you think you work through the mushball system, that, you know, if you have something driving that, in fact, you have latent heat being released, and that will then lead to more motions and so on. So, you know, again, nonlinear feedback systems, which is really what I think chaos is about. But if there's an atmospheric scientist on this call who knows better than me, please speak up. I'd love to hear what you have to say.
I don't think there's an atmospheric scientist on the call who's better than you, who knows more than you on this, but there might be, and please do speak up if there is. That right now is that was the last question that I have. Does anybody else have any questions they'd like addressed?
There are some actually in the Q&A. I don't know whether you saw those.
No. Oh, Q&A. Oh.
Oh, there's a lovely one here. Can I read that one out? Yes. How likely is it that we can obtain evidence to support or deny the existence of microbial life on Europa? That is the next mission. Okay, so the Europa Clipper, which is being built right now at the Jet Propulsion Lab and the instruments in different parts of the country, across the globe, in fact, is going to be put together, and it will go into orbit around Jupiter and fly past Europa multiple times and take really close-up images of Europa and get a sense of what is the brown gunk that you see on that icy layer. So we know that Europa has an ocean underneath the ice, and we measure that using the electrical induction. Okay, so we measure the magnetic field as we fly past Europa, and what we see is there's a perturbation due to electrical currents that are flowing in the ocean of Europa. So we know this, that it has liquid ocean inside. Thick layer of crust, and then there are cracks, and the cracks are brown. And what is the brown stuff that seems to be coming from the inside out? Could it be whale poop? Probably not whale poop, but it could be microbial life. It could be quite complicated life. We don't know. Maybe there are black smokers deep down with the tidal heating causing eruptions and gases mixing in with the water, and that eventually leads to life. Could well be. We think that's one way in which life formed here on Earth. So Europa is definitely the place in our solar system outside the Earth where we may find actual life, existing life. The Europa Clipper mission will tell us where is the most likely place to find the liquid water getting up from the ocean, and it will tell us the thickness of the ice and where it might be thin, and it'll tell us what that brown gunk is. And then we can go back with a lander and scratch and sniff the brown gunk and maybe detect microbes. So that's down the road. Yeah. Great question.
So Doug Phillips asks, what kind of costs are involved with extending the mission, and what will the money be spent on?
So it will be spent on us, the scientists. So yeah, some of my salary, my graduate students and researchers who analyze the data, some of the operations people at JPL who operate the spacecraft, the people at Lockheed Martin who communicate with the spacecraft and send the instructions up and so on. And so it's people. This will employ people to continue doing the work that we're doing. And so the whole mission was $1 billion, like I said, cafe latte per taxpayer. And I don't know the exact numbers that we're talking about, but it's a fraction. If you think of a typical space mission, something like 80 to 90% of the cost of a space mission goes to the engineers and the managers, and something like 10% goes to the scientists, to be honest. And that's not because we're cheap. Well, we are fairly cheap compared with engineers, but it's because, you know, they have to build the spacecraft to make it work. And then we just, our time is sort of stretched out over a longer period of time. So that's where the money would go.
Yeah, it's interesting, Fran, because the system in the US is very different than the system in Canada. And at some point in time, I'd like someone to come and give a talk about the senior review process because it to a lot of people it doesn't make sense to shut down a mission, because the relative cost of keeping it going is so small compared to the cost of building it and launching it and all of that. But that senior review process keeps things healthy.
Yes, it's very healthy because it makes us think. We spent the best part of 9 months writing an extended mission proposal. It got us thinking, what if we did this? What if we did that? Could we do this? Could we do the other? And what would be the best way for us to get the optimum science out of the rest of the mission? And that got us to think about, are there ways that we could be more efficient, which is always healthy? Could we think of streamlining the process to make it more cost effective? And so I actually think it is a healthy process. Yes, you're right. You're right.
Well, I mean, there's a couple more questions, but you were involved in Voyager, right? And Voyager still does well in the senior review process.
Well,
right?
You're not going to turn Voyager off. Come on.
Right. So, Tom.
And it costs very little to keep it going. It costs very little to keep it going, right?
Yes.
And it's out there in the interstellar medium making a few measurements. It takes 18 hours to get the signal back. Isn't that amazing?
I know,
it's out there.
It's fascinating. And so Tom Gallagher has asked a second question. Gravitation synchrony of the large planets may contribute to the sun's energetics. The regular periodicity of 11 and 88 years in the sun's activity is important to the Earth sciences.
Well, I don't know. I agree that Jupiter has the most mass in the solar system, substantial amount, but it's still considerably less than the sun. I'm not so sure. You have to be very careful with periodicities. Partly because if you look at the sun's activity, it's not super regular, actually. It's not like an orbit where you have a very regular orbital period. The sun's activity periods are a kind of fuzzy. They come and go. And looking at the current solar cycle as an example, it's sort of stretched longer, and sometimes they're bigger and sometimes they're less. So you have to be a little bit careful with periodicities. And just because you see a periodicity, correlation is not causation is the phrase that people use. You've got to be really careful. And I don't know about you, Eric. What do you think about the solar activity being triggered by relationship to Jupiter? I find that a little hard, a bit of a stretch, to be honest.
I mean, so I agree. I mean, I find it a bit of a stretch. The flip side, though, is we don't really understand a lot of the sun's dynamics, right? And the idea of very small perturbations that are, in some sense, consistent, right? And so I wouldn't dismiss it, right? But I would say I don't think it's very likely, but that's not the same as knowing that that's not playing an effect, right? And so it's that's where I would sit on that. But so Robin Owens,
great question.
Yeah, Robin Owens asks, there was a recent paper about the discovery of phosphine in the atmosphere of Venus. Do you believe that this is plausible evidence of microbial life?
Nah. Carl Sagan talked about life in Venus's atmosphere way back when, 40 years ago, something like that. And I didn't really buy it then. It's really hard to see how you can make life outside water. You kind of need to have water because of the properties of water and the density of water and so on. It's kind of hard to make molecules bump into each other and make enough of stuff. This new discovery, the paper actually does not make it, it just raises it as one option of how it might be there. And people have press has gone off and run with it. I've actually read some various papers that have other suggestions how you could make, and I'll bet you in the next few weeks there will be a bunch of papers coming out with alternative explanations. On the other hand, I'm a big fan of sending one of the next missions to Venus. Venus is a really neglected planet. It's our neighboring planet. It's the same size as the Earth, and yet it's unbelievably inhospitable, very high temperatures, runaway greenhouse effect. And I'm not saying this because I have anything in that mission. It doesn't have a magnetic field, so it doesn't have a magnetosphere. So I'm not pushing this for my own benefit. I'm pushing this because I think as a planet, understanding on our sister planet that has a runaway greenhouse would be really interesting and really useful. So I think we should go there. And this discovery of phosphine was kind of convenient to help us push the next mission to Venus.
Yeah, and Jim Green came here and gave a Gallagher lecture last year, and he had, I believe, had said that Venus used to be in the habitable zone. That the habitable zone has evolved over time in the solar system. Could
be. The problem is with the term habitable zone is, look at Europa, the most likely place that we have life. It isn't in the habitable zone. Right. So it's a phrase that's bandied around, and I'm not sure how useful it is.
Okay, so we have one last question from Robin Owens. It's the second question from Robin. Why is Jupiter so large? Is it because it is the first planet to form outside the ice zone, or is it more complicated than that?
I think that is the answer. Now, before this complexity of not quite understanding what's going on inside Jupiter, I would say, yes, absolutely, of course. So there's a little bit of doubt sown by the new results at Jupiter with this distributed interior. But I think absolutely that it's a runaway, you know, it's called oligarchic growth, right? So once you get large, you have more gravity and you can suck in more. So it's again, a nonlinear feedback system, which there are many in our universe. This is another example of that. And so I do believe that indeed it is large because it's the closest object in the ice zone, beyond the snow line. And so it was moving faster and could quickly around the sun and could pull in lots of stuff, and it was denser, and so it just got bigger and bigger and sucked in the hydrogen, and then it started pushing all the other planets around, and it was the master of the solar system. So
you're saying it's so large for the same reason that Amazon is large and Google is large. You know?
Nonlinear feedback systems. Nonlinear feedback systems.
Yeah. And so, okay, so we're done with the post-formal part of the program. And so my closing comments are thank you, Fran, for your presentation and for answering our questions this evening. Thank you to everyone who decided to stay and continue the conversation with our speaker. It has been great being able to be here this evening. Remember to check the Faculty of Science website, science.ucalgary.ca, for information about upcoming talks and the recording from today's event. So thank you again, and have a great evening, everyone. And I look forward to doing this again sometime in person.